Welcome everyone to my presentation titled Building AI-Powered Applications on Microcontrollers with TensorFlow Lite Micro. My name is Marcin Ochman and I'm Senior Edge Machine Learning Engineer at DeepSense AI. And today we are going to explore how we can leverage the power of artificial intelligence in highly resource-constrained environments like microcontrollers. Together, let's explore the fascinating world of embedded systems enriched with the power of AI. So let's get started. To outline today's presentation, we will first delve into an introduction to microcontrollers and edge computing. Following that, we will carefully examine the layered architecture behind AI-powered applications for microcontrollers. I will then guide you through technologies like FreeRTOS and LVGL and elaborate on how TensorFlow Lite Micro is seamlessly integrated into that ecosystem. And lastly, we will culminate with a practical demo showcasing real-world application and conclude by summarizing the critical takeaways from that presentation. So let's move to the first part of that talk, which is the introduction to microcontrollers. So edge computing is a paradigm that moves computation and data storage closer to the source of data generation. And in the context of AI, this means that running AI models runs directly on device rather than relying on the external cloud servers. There are many examples of edge devices, and one of them is microcontroller. And I think that microcontrollers is a perfect example of edge computing because it is highly constrained device. On a related note, I previously gave a deep talk 1 year ago about the edge AI focusing on mobile devices like smartphones. So if you're interested in exploring how AI operates on Android devices, I would recommend you checking it out for additional insights. And to better understand the problem, let's begin with some basic definitions. A microcontroller is a small integrated circuit that includes a CPU, memory, input-output interfaces, and often analog to digital converters and digital to analog converters. And these devices are typically used in embedded systems, which are computers designed to perform specific, often real-time tasks. And for example, a microcontroller might power your smartwatch, thermostat, or even your car's sensors or other devices within the car. And what makes them particularly interesting is their ability to run AI models despite having so limited computational power and memory. So this ability opens up new possibilities. However, building microcontrollers application, especially with AI, may be a very challenging task. So let's dive deeper into that problems. So running AI on microcontrollers comes with unique challenges, including limited memory, low computational power, often which comes with the real-time requirements. And these devices also lack operating systems and memory management units. So that makes the development even more complex. Developers have to manually manage memory allocation, which is basically challenging in systems where every byte counts. And without an operating system to handle multitasking, programmers must design and implement task scheduling themselves, ensuring that processes like data acquisition, preprocessing, and inference don't interfere with each other. So this complexity demands careful planning and a deep understanding of the hardware. And furthermore, integrating AI into such constrained environments requires significant model optimizations. techniques like quantization or pruning and the use of lightweight architectures become very, very important. And unlike on PCs or smartphones, where high-level frameworks abstract much of this work, microcontroller-based AI development requires a more hands-on approach. Overcoming these difficulties, however, is very rewarding because it enables many advantages that we will see in a moment. The advantages of using AI microcontrollers, I would say they are significant. So these benefits include real-time decision-making, cost efficiency, and enhanced privacy. So let's get deeper. Let's explore those in more detail. Processing data locally on microcontrollers reduces bandwidth usage and enhances privacy by keeping sensitive data on the device. And furthermore, AI enables real-time decision-making, which is critical for time-sensitive applications, like, for example, anomaly detection and voice recognition. Additionally, microcontrollers are also cost-effective, and so that makes them a practical choice for resource-constrained environments. And advancements in AI have made it feasible to deploy more powerful models even on such constrained and limited platforms. So for this presentation, we are using the STM32H74 Disco board. It is powered by a dual-core ARM Cortex-M7 and M4 microcontroller. However, in my demo, I only use the first one. It has 2 megabytes of flash memory and 1 megabyte of RAM. It also features the touch LCD. It also has audio capabilities and multiple user interface components like LEDs, joystick, and push buttons. So basically, those components makes that platform a very good board to develop and test AI applications on microcontrollers. And to put this into perspective, let's compare microcontrollers to other devices like mobile phones or PCs. Modern smartphones often have several gigabytes of RAM and high-performance processors, making them capable of running advanced AI models like language models or standard computer vision models. PCs, on the other hand, can handle this task even more effortlessly. In contrast, our board has to operate with just 1 megabyte of RAM, which is very, very tiny compared to the memory requirements of the common AI models. So, for example, many vision models require tens or even hundreds of megabytes of memory, and LLMs like Llama 3 require even several gigabytes. So the challenge lies in the choice of small models and optimizing them to fit within these constraints while maintaining their accuracy and preserve their functionality. So this highlights the difficulties of deploying AI models on microcontrollers. Microcontrollers can handle various AI applications, such as voice tasks like word detection and voice recognition, sensor data analysis, for example, for predictive maintenance, and computer vision tasks like image classification and gesture detection. These applications demonstrate the flexibility and utility of microcontrollers in deploying AI-powered solutions across various industries. However, it is important to note that these AI applications are often very simple and task-specific due to the limited resources of microcontrollers. So, for example, a microcontroller might only be capable of detecting a single phrase like high deep sense AI rather than supporting complex and more generalized models. Okay, so now let's see how we can build applications for the microcontroller. This slide illustrates the layered architecture used to deploy AI models on microcontrollers, showcasing how multiple layers work together to enable efficient operation in the resource constrained environments. At the bottom, we have the hardware layer, which includes, of course, the microcontroller and its peripherals. Above that, we have a Cortex microcontroller software interface, which provides the essential software components only for the ARM-based microcontrollers, ensuring that the access to the hardware is standardized. The next level includes hardware abstraction layer and the board support package. And these components abstract the specifics of the hardware, making it easier to write portable and reusable code across different platforms. HAL ensures that the developers don't need to deal with low-level hardware details directly, while BSP provides drivers and configurations as specially tailored for the dedicated board. So in our case, the STM32H747 Disco board. Moving upward, FreeRTOS is the real-time operating system layer. And this layer is responsible for task scheduling, resource allocation, and of course, synchronization between tasks. And FreeRTOS ensures that real-time constraints are met while managing the limited resources of the microcontroller. And it is worth noting that FreeRTOS is, or even no matter which RTOS, it isn't strictly necessary for the microcontroller applications, but it significantly simplifies the architecture and especially the management of complex applications by providing structured multitasking and efficient resource handling. So without the RTOS, developers would need to manually handle timing, task priorities, inter-task communication, and that could be very error-prone and cumbersome, especially in the complex and sophisticated systems. At the application layer, we integrate AI models using TensorFlow Lite Micro, and we leverage the LVGL, lightweight GUI library. So LVGL handles LVGL is the GUI library, so it handles the touchscreen interactions. It also handles widget rendering, GUI animations, and of course enables the interactive user experience. TensorFlow Lite Micro acts as the inference engine, executing optimized machine learning models, and together those components form a seamless interface where AI-driven functionalities and user interaction coexist efficiently. Additionally, the dashed line in the architecture indicates that those are optional components. So that means that depending on the application, certain features like LVGL for GUI rendering or specific AI functionality may or may be not included or just changed to other library. And this layered approach is particularly important because we will create a similar architecture during our demo. And let's move to the FreeRTOS. And FreeRTOS is a lightweight real-time OS designed for embedded systems, and it supports preemptive and cooperative scheduling. It also manages tasks very efficiently, and it also provides the inter-task communication. So FreeRTOS is a key to manage multiple tasks on microcontrollers, and it ensures that our resources will be used very efficiently, and will be able to run our application with the real-time performance. The main components of FreeRTOS used by developers are tasks and queues, and the slide features a figure with two tasks, where task 2 sends data to task 1, and this communication is implemented using FreeRTOS queues, and they serve as a safe and efficient mechanism for exchanging data between tasks. So task 2 places a message in the queue, and task 1 retrieves it when needed. So it ensures that mechanism ensures that the synchronization is without blocking execution. So another useful library is LVGL, as I mentioned before, and LVGL stands for Light and Versatile Graphics Library. And it is an open source GUI library, especially optimized for embedded systems. And as I said before, it offers full support of touchscreens, a wide range of widgets, and of course, it is compatible with various devices. So basically, LVGL allows us to create very intuitive interfaces, especially for the microcontrollers. Okay, so now it's time to focus on AI models, and especially on the TFLite Micro. So TensorFlow Lite Micro is a version of TensorFlow Lite, and it is designed especially for microcontrollers. And it features a small memory footprint, supports cross-platform architectures, and optimizes inference through techniques like quantization or pruning. And it is designed to work without an operating system, and it makes it suitable for for bare metal or RTOS environments. So this flexibility allows us to deploy various machine learning models directly on the microcontroller. And while TensorFlow Lite Micro shares many features with TensorFlow Lite, such as quantization of the model and efficient inference engine, there are some differences. And TensorFlow Lite Micro is specifically tailored for devices with extremely constrained resources, offering no dynamic memory allocation and requiring developers to define a static memory arena upfront. Unlike TensorFlow Lite, it doesn't support operations that require large intermediate buffers or complex model architectures such as large language models. Instead, it excels in deploying simpler models like CNN or fully connected networks. So basically, the TensorFlow Lite is optimized for such tasks like voice detection or gesture recognition. And these distinctions make TensorFlow Lite Micro an essential tool for microcontroller applications. So the deployment process starts with training a model in TensorFlow. This involves feeding, this involves feeding a dataset into a neural network, allowing to learn patterns and generate accurate predictions. And once the model is trained, it is converted into TensorFlow Lite format, which optimizes it for resource constrained environments. By doing two things: by reducing the size of the model and trying to optimize the model in terms of performance. And after conversion, further optimizations such as quantization are applied, and this step is crucial for ensuring that the model can fit with the limited memory of a microcontroller. Next, the optimized model is embedded into application as a C array. And this step converts the model into a format that can be directly integrated into the microcontroller's firmware, and it allows to be used for inference without relying on any external dependencies. And finally, the model is deployed on the microcontroller, where it performs inference locally using, of course, TensorFlow Lite Micro runtime. So now let's take a closer look at the process of converting and optimizing a machine learning model for microcontroller deployment. And the code snippet here demonstrates how to use TensorFlow Lite to convert a TensorFlow model into a lightweight format, which is suitable for edge devices. And the process begins with the initialization of TensorFlow Lite converter. And this step prepares the model for conversion by defining its structure and weights in a way that TensorFlow Lite can understand. Next, we apply an important optimization step using by specifying the optimization array, and that enables post-training quantization, reducing the model size and improves the inference speed. And once the optimization are set, the convert function is called to perform the actual conversion. And as a final result, we get the TFLite model that is significantly smaller and more efficient than the original And at the end, we can save our TFLite file. We can save our TFLite file on the disk. Okay, and now let's take a closer look at the process of deploying a TensorFlow Lite model onto a microcontroller. After converting and optimizing the model, we need to embed it directly into our firmware. So this is done using the XXD tool, and that transforms the TFLite binary model into a C array that can be included in our embedded system code. So the command converts the binary file into a C source file, which defines the model as a constant byte array. So this is necessary because microcontrollers lack traditional file systems, so the model must be stored somehow in the program memory. And the resulting model C file contains an array definition like that. To initialize a TensorFlow Lite Micro model and configure its runtime, we need to set up a few components that enable machine learning on microcontrollers. So the TFLite Micro runtime provides essential C++ components for executing models efficiently on low-power embedded devices. This includes the interpreter, which is responsible for loading and running the model while managing the tensor data, and it also executes operations step by step. We also have the resolver, which plays a crucial role in mapping TensorFlow Lite operations to microcontroller compatible implementation. And finally, we have microtensors, which represent basically the multi-dimensional arrays used by the interpreter during inference to store both input and output. What is worth mentioning here is that we have to load the model, and to load the model, getModel function is called, and we pass the gmodel data variable, and that gmodel data variable is our dumped model into the which was dumped model into the C file. So this is basically the binary array holding the whole TensorFlow Lite model. Okay, so now let's talk about how we actually run the inference. First, we need to provide the input data and in TFLite Micro, input tensors act as a placeholders for the data. For the data which is the input. So basically, first we have to assign values to the input tensors, and for that we can use the input method. And as you can see here, we set the first input tensor by assigning a value t, and this step ensures that our model gets the correct input before running inference. Once the input is set, we need to execute the model, and this is done using the invoke method, and calling invoke function tells the model to process the input data and run the inference. And at this point, the microcontroller will compute the model's output, and of course, when the inference is finished, we are able to retrieve the results from the model's output tensor, and for that we can call the output function. Okay, so now that we have covered the key technologies and many concepts, let's move to the practical aspects with a closer look at our demo. So the goal of our demo was to showcase the capabilities of microcontrollers. Specifically, we aim to assess their performance and demonstrate the integration of TensorFlow Lite Micro with FreeRTOS and, of course, the LVGL library. So we wanted to use both the two models, the prediction model and the detection model, to highlight practical applications. And as you can see on the right, there is a photo of microcontroller running the prepared application. And in that application, two models are running. And as a user, you are able to choose between two screens displaying the current status of a particular of the specific model. So here's the big picture of our demo, and two tasks are related to the inference, and that means that prediction task is responsible for running the prediction model, and while the detection task, as you might expect, performs the inference of the detection model. And detection model is a word detection model which uses the audio samples. So as a consequence, we have to collect the audio samples from built-in microphone, and that process involves the collection first of the PDM samples. Then we have to convert them to PCM and store them in the dedicated audio buffer. When the audio buffer is filled, then the message is sent to the detection task, and it can start the inference. On the other hand, there is a prediction task which performs the inference every 50 milliseconds. Okay, and as you can see, here's how the demo works. We have the model, and the model can estimate the values of the scene function. So as you can see, our dot follows the scene curve. Okay, let's move to the next one. Okay, so here's the basic code for the prediction model, and on the right you can see that how the prediction task code runs. So it runs every 50 milliseconds. Then, if the results is ready, we send over the queue, the message over the queue, and the GUI is able to update the screen. And here, I think it is much better model because here we have to detect the yes word, and I will show you how it works.
Yes.
So as you can see, the model is able to detect the yes word, and if the model detects that, then the GUI is updated to show that that yes word was detected. Basically, that model is much more complex than the previous one because it uses the convolutional neural network. And the input of that model are the features which were calculated based on audio samples from the window of 1 second, and those features are called MFC.
Yes.
Okay, and here's the another example of the code. Basically, the approach is almost the same. What you have to remember is that we have the mechanism where you have to notify our detection task that audio samples are already in the buffer. So there is one difference between the detection task and prediction task. In detection task, we wait for the new message, which informs us that there is a new audio samples that need to be fit into the model. And to wrap up our discussion, let's take a moment and reflect the key takeaways from this presentation. First, despite the microcontrollers' limited computational power and memory, microcontrollers are fully capable of running AI models. Another important point is that it is possible to deploy multiple AI models on a single microcontroller. A major advantage of AI on microcontrollers is that it enables local inference, and by processing data directly on the device, we can reduce latency and eliminate dependencies on our cloud services. And while the deployment process for TensorFlow Lite Micro is relatively straightforward, it does require a solid understanding of the build system, configuration, and the hardware itself. And finally, Edge AI is still rapidly evolving, so I would expect that as hardware continues to improve and AI models also will become more efficient, so we will be able to do even more on the microcontrollers. That would conclude my presentation. I hope that this session gave you a brief overview of how we can build AI-powered application on modern microcontrollers, especially with using the TensorFlow Lite Micro. And yeah, that would be all. Thank you for your